Hey, fellow mathers. Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam-packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over $6,000 worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, mathematicians, or fellow mathematicians. Hey, fellow mathematicians. Welcome to the podcast where math is figureoutable. I'm Pam.
And I'm happy because Pam messed it up today, not me. I'm Kim.
And you found a place where math is not about memorizing and mimicking, waiting to be told or shown what to do, but it's about making sense of problems, noticing patterns, and reasoning using mathematical relationships. Y'all, we can mentor students to think and reason like mathematicians. Not only are algorithms not particularly helpful in teaching mathematics, but rotely repeating steps actually keep students from being the mathematicians they can be. There, I got that part down. Holy.
Welcome back, everybody.
Hey, Kim.
So a special good morning to Susan Smith. I know you're listening because she sent a review and she said, I listen to multiple math podcasts, but Math is Figureoutable is one I never, all capitals, miss. I have binge listened to many of the past podcasts I missed before I discovered it, and now I never skip my weekly listen to the latest episode. I always walk away with a new insight or deeper understanding that will make me a better math teacher and a better mathematician. There are even powerful episodes I have listened to more than once. Don't miss out. You'll always be glad that you tuned in. So Thank you. Thanks, Susan.
Susan, that's super nice. Kim, this is super fun when I don't hear them before you.
I know. I told you.
Yeah, that's cool. All right. Thanks.
So, hey, if you're a new listener, I would encourage you to go back and check out some of the old episodes that sound interesting to you, right? So we're on episode 174 already. Can you believe that, Pam? 174.
Bam.
And some are in a series, but you don't necessarily have to go in order for all the other ones. You can pick and choose what sounds interesting to you. And if you're like, no, really, Kim, Pam, where do I start? You can check out episode 156, and that title is Start Here, and that'll give you some big ideas about the Math is Figureoutable movement.
Cool.
All right, let's get going. We've been long-winded the last couple of weeks.
All right, no, today we're down and dirty.
We're being serious today.
Getting her done.
All right, so Pam, I know I
believe that.
I know, and I'm telling a story today, so maybe that'll speed things up.
Oh, you're saying you tell stories faster than I do. Is what you're saying. That's what you're saying.
I can be wordy, but I feel like you might be a little wordier than me.
I don't know. Okay. Would I say you're wordy? I don't know if I would say you're wordy.
Tell my family that. Okay.
Right.
So you actually know the story. So I'm just going to tell it for the benefit of the listeners. So I was in a 4th grade class doing a problem string. I don't know, it's been a year or so. We were doing some filming. I was getting a couple of different strings, and we did like the first 2 problems of a string for this particular strategy that I was going for. And I was asking students to describe the model that I was using. And one kid said, oh, you're doing the blah, blah, blah strategy. And then he said, but I don't know why you would ever do that. And I was like, oh, okay. He was kind of a little sweet kid, but he was kind of a little arrogant about it. Like, that's not for me. And frankly, it didn't bother me. I kind of leaned into that thing and we kept going.
Yeah, you don't mind snark. You don't mind snark at all.
No, not at all.
You know, it's interesting, Kim. I remember watching the video because I wasn't there on the filming day. And I remember watching the video and going, oh man, he like already owns the strategy. Like this is going to fail. And so when you kept going for just a second, I was like, why didn't you just stop and do something else? It's not going to work.
Yeah.
So
Yeah.
Let's talk about how that went maybe a little bit later in the
Okay.
podcast.
All right.
Yeah.
We'll finish up.
So let's work on that strategy that you were working on with that particular class
Okay.
and have some fun with that. Oh, Kim, I just realized hang on. I don't have enough paper.
Oh.
There's no way this particular problem string is going to work with that little square of space. Surely I have a blank piece of paper in this pile of paper. Do you know what I've started doing? You don't even know this.
What's that?
I've started just taking copy paper.
Oh,
And
that's
I
what
have
I use.
Well, I know. See?
Oh.
And so I didn't ever used to do that. I used to use, what are those called? Those 9x11
Those
legal
little yellow
pad things?
pads?
Yeah.
Yes, I hate
And
those.
with and I ran out of them. And I had copy paper and I was like, I'll be Kim. I'll just be Kim. Now I put mine on a clipboard. I think yours is just loose. Is that right?
Yeah, it is. It is.
Yeah, mine's on a clipboard. Okay. All right. First problem 15 times 18. Have fun with that one because
Ooh,
there's so
okay.
many nice things you can do with that one.
Super. Oh my gosh. You don't have anything in mind? I can do what I want?
Yeah, do what you want.
Okay. I'm gonna go with 10 times 18, which is 180. And then I still need 5 times 18. And I know 5 is half of 10. So if 10 18s was 180, then 5 18s is going to be 90. So together that is 270.
Bam. Nice, smart partial product. Nice using 5 is half of 10. Cool. So 15 times 18, you're saying is 270.
Indeed.
Next problem.
Yep.
What is 9 times 30?
9 times 3 is 27. Times 10 is 270.
So 9 times 30 is 270.
Mm-hmm.
So we now have two problems that have the same product. And I know you guys are listening, so I'll just say it again. We had 15 times 18 was 270.
Yep.
And you just said 9 times 30 is also 270.
Yep.
Kim, are those two problems related? If I were to draw, so you mentioned...
I'm literally sketching as you say, if I were to draw...
Yeah, so you mentioned you asked that kid in class to talk about the model.
Yep.
So I have a 15 by 18 on my paper. If I were to draw a 9 by 30, based on that 15 by 18, could you help me? What would the 9 by 30 look like?
Sure. So I drew, it's like kind of squarish, but a little bit longer on the 18 side. So 15 down and 18 across is what I have. Is that what you have?
Yes.
So so across the top I had 18, but now I only want 9 across the top. So I'm cutting that 18 in half and just kind of drew a dotted line down mine, cutting that 18 in half. So it's like a 9 and a 9 by 15. And I'm going to move that second half of that squarish one. It's not square, but you know what I mean. And I'm moving it down. So I'm making it twice as long and half as wide. My 9 by 30's half as wide and twice as long as the 15 by 18.
So you actually just created a 30 by 9.
Yeah.
Yeah. Even though I said 9 by 30. So maybe I shouldn't have asked you. I should have just told you. Let me tell you what I would have put on the board. So I loved your explanation. It makes a lot of sense. You cut the 15 by 18 in half. You moved half of it down, created a long, skinny rectangle, a tall, skinny rectangle.
You want me to make it be 9 by 30? Is that what you want?
If I was running the problem string, I would have drawn a 9 by 30 and I would have said, so how does the 9 relate to the 15? And you would have said, well, not a little bit more than half. I don't know. 9. And then the 30 would have been not quite twice as long as 18. So you would have had this long, skinny, but horizontal 9 by 30. Is that right?
Yep.
And then I would have said, all right, so we're agreeing that they both have the same area of 270. Can you make that fit?
Yeah.
So would you mind describing from the 9 by 30, that horizontal flat-ish rectangle, how would you move from it to the 15 by 18?
So that in that case, I would rotate it
to create the one that you ended up with.
Yeah.
Yeah. And then you would have kind of that 30 by 9, and then you could have done the same kind of cut in half thing and everything. So that seems like important, that if you cut one of the dimensions in half and slide that bit of area down to make a long, skinny one, which then in effect doubles the other dimension, you didn't lose any area. And we ended up with the same product. I wonder if that happens all the time. That's what I would say to students. Yeah. Next problem. How about if I asked you 4.5 times 60?
So I'm looking at my previous problem and I'm noticing that 9 is twice as much as 4.5. So I'm sketching, and so right below my 9 by 30 that you had me draw,
Mhm.
I'm
Mhm.
drawing 4.5, but it's only half as long on the 4.5 side. So I'm gonna actually make it be 60 long, and it kind of is off my paper, so I drew some dots. But a 4.5 by 60 is skinnier than the 9 and longer than the 30.
And skinnier by how much?
Half,
And longer by
double.
double. Cool. So you kind of halved one dimension, doubled the other. What is? Did you ever find 4.5 times 60?
Oh, I didn't. But it's also 270.
And how do you know it's 270?
Because if I cut that 9 by 30 into two pieces to make it be like a 4.5 by 30 and a 4.5 by 30, I could take that bottom 4.5 by 30 and slide it to create a 4.5 by 60. So I didn't lose any area.
So we have an equivalent problem, huh?
Yeah.
It seems like you've created equivalent problems all the way along. You've got 15 times 18 is
Mhm.
equivalent to 9 times 30, is equivalent to 4.5 times 60, is equivalent to 270. So 3 equivalent problems where you're kind of talking about cutting one dimension in half, doubling the other dimension, and the area stayed the same. Therefore, the product stayed the same. That seems kind of helpful.
Mhm.
I wonder if you could do something like that for a problem like 24 times 3.5.
Yeah, I was trying to make it relate for just a second.
Mhm. I mean,
I
it might, and it might
yeah,
not, right?
yeah. I'm okay. I don't really love the 3.5, so I'm gonna double that one to make it 7.
Okay.
And so that I can maintain the same area, I'm going to have the 24 to make that 12.
Okay.
And so that is 84.
Do you just know 12 times 7?
Um, yeah, I do.
That's okay.
Why do I say that like it's a disappointment? Yeah,
Because you want
sorry.
because you want to be able to talk about how you
I
think
do.
about it, and you're like, darn it, I just know that one. Hey, y'all, just take a minute. Just take a minute to appreciate that that's mathing. It's mathing to say to yourself, ah, crud. I wish I had a way. I wish I had a reason right now to tell you how I'm thinking about that. And darn it, I just
Yeah.
know that one.
Yep.
Wouldn't you love it if that was the result in your classroom where kids instead of go, like, how often do we hear them go, I just know that one? And you're like, yeah, but tell me how you think about it. No, I just know that one. Instead, we're like, oh, crud. I just know that one. Oh, man. That stinks. Darn, I wish I didn't just know that. I
That's
think
funny.
that's awesome. Okay, cool. So you could double one of the dimensions, half the other. That you're saying that you could like take that area, slide it over, create this
Yep.
new rectangle that would be a 12 by 7. If you didn't know 12 by 7, which I'll just be honest, I have to refigure every time.
Oh, okay.
I know, yeah. So I often just think about 10 times 7. And as soon as I have, so like 12 times 7 is like 10 times 7
Yep.
plus 2 times 7, but I don't do that much work. I literally think about 10 times 7 and I go 70, 84.
Yeah.
Like I don't even think about that I need 2 more or whatever. It tells me, I know that I'm going to be 60 for 12s, that I'm going to be 60, 72, 84, 96. And I can just never remember which one's which.
Yeah.
And so,
Oh,
oh
that's like
yeah.
that's me for 8 plus 5.
Is
Like
that,
I think we
what do
all
you mean?
have the I for whatever reason 8 plus 5 I'm like, is that 12, 13, 14? I don't but I go back to the fact that I know 8 and 4 is 12 for whatever reason. That was my favorite fact as a kid. So then I'm like, oh, it's 12, 13. Is that
So
weird?
then
Yeah.
8 plus
So
5 has to be different. No, you're
yeah.
reminding me actually. So I was just in Oklahoma a couple weeks ago, a few weeks ago. I don't know how long ago. Anyway, had a super group of people. And Kathy, the calculus teacher, when I said, does anybody not know 8 times 7? And you can admit it, whatever. And I always love it when it's the calculus teacher that
Yeah.
raises their hand and goes, yeah, I don't know it. And she goes, yeah, I just can never remember if it's 54 or 56.
Yeah.
So she refigures. I can't remember exactly what she does, but I think she refigures 9 times 6 and then says, oh, it's not that. So it's
Yes,
like
that's the 54, so it can't
yeah,
be
she
that.
goes,
Yeah.
oh, that's 54. So therefore it's
Yeah.
56. Like that was her.
Yeah.
I think Kathy, hopefully I just
I
gave
want
you
lots of
credit there.
adults to admit that.
I
I want
mean,
lots of adults to say, you know what? Like I have to refigure one in a mathy way and it's okay.
and it's more than okay, because
Yeah.
what we're saying is don't fill your brain with that trivia. Fill your brain with relationships.
Yeah.
so that you can refigure it in an efficient enough manner that it doesn't bog you down in the work you're doing. And at the same time, because you are using relationships, your brain is more developed and you can do more and all the things. Yeah. Okay, cool.
Back to the problem string.
Next problem. How about 32 times 12.5? I mean, Kim, now I'm giving you a 2 by 3 multiplication with decimals.
Yep. So I again don't love the 12.5. So I want that to be 25. So I'm going to create the problem 16 by 25 by halving the 32 and doubling the 12 by 5.
Okay, 16 times 25.
Uh-huh. And
Yeah.
I actually know that one. I have done enough work with quarters, but
Sure wish
at
I knew
that
something about quarters. I'm quoting Kim, by the way, there. We have a video of Kim working with fourth grade kids, and this kid says something about 25. So she goes, sure wish I knew something. Or no, you
Yeah.
said something like, what do you think about? And he goes, quarters. And you go, sure wish I knew something about quarters. Anyway, sorry, keep
Yeah.
going.
So if at that point I didn't know something about 16 by 25, that's still a really nice problem because if you double and half again, then you get 8 by 50, and you could even do it again and get 4 by 100.
So you're saying 4 times 100 is 400, and 8
Mhm.
times 50 is 400, and 16
Mhm.
times
Mhm.
25 is 400. Therefore, 32 times 12.5 is also 400.
Yeah. Yep.
So you created lots of equivalent
I did.
problems to solve that sucker, even though you probably could have only created one.
Well, and it's funny that we're having this moment right now because I have one of my boys is absolutely obsessed with double half. He wants to like it's kind of like over for him. Like he seeks for that everywhere, and I have to say to him like stop when you get to one that you know, like that you because he wants to just like and I know this and I know this and all the way down to like times one or whatever. Like hey, okay, you can stop when you know
Kim,
that.
let
I
him
know.
play. Let
I
him
know.
play. So you're not really commanding. You're not like
Oh gosh,
you're
no, no,
not
no, no. I'm
slapping his
like,
hand and
no,
saying,
I'm like, do
stop.
you know that one? He's like, yes. Like, okay, all right.
Hey, Kim, this is reminding me that in a recent Q&A for our online workshop. So we have
Mm-hmm.
online workshops. We have live Q&As.
Uh-huh.
Participants get on. They can ask questions. One of the questions that a participant asked was, what are problems that are reasonable to solve without a calculator? Because I will
Yeah.
often say, if you help develop the major strategies that lead to the major relationships, then you can solve any problem that's reasonable to solve without a calculator. And she said, I think it might have less to do with the number of digits, like how big the numbers are, and more to do with the numbers themselves. Am I right?
Yeah.
And my answer to her is absolutely,
Yeah, that's
because
great.
we have standards that say things like for example, fifth grade. Often in fifth grade, the standard is no, sorry, fourth grade is what I'm thinking of, where the quotient is 4 digits and the divisor is 1 digit. So it's
Mm-hmm.
like don't go above those. 4 digits divided by 1 digit, and I would say it absolutely depends on the numbers. For
Yeah.
example, 32 times 12.5 is a 2 by 3 multiplication that I think we could do in fourth grade once kids
Yep.
learn to double and half.
Yep.
So it's way out of their standards because they're not doing decimal multiplication in fourth grade, but it's doable because of the numbers. So yeah,
Right.
it's more important to think about the numbers and less important to just randomly the size of numbers.
Mm-hmm.
Yeah, cool.
Yeah.
Next problem. Could you do a similar thing? By the way, it's the last problem, Kim. You can do it. You can do it.
Okay.
1.75 times 36.
Um, okay. So I'm gonna go with doubling the 1.75. And I
Okay.
think about that like $1.75.
Yeah.
So double $1.75 is 350.
Do you want to do you just know that one? I don't know. We might have to.
150 and 150 is $3, and I have an extra quarter. So I thought about the 175 as 150 and 25 cents.
And you doubled both of
So double both
those.
of those to get $3.50, which is
Cool.
350.
Thanks for doing that. Uh-huh.
And what was the other? What was the other? I don't even know. I think you said
36. Aren't
36.
you glad? Aren't you glad? Yeah.
Yeah. So then I would think about that like doubling that again, double half again, I think. So then I would get
Wait,
three.
sorry. So hang on. Oh yeah. Forgive me. Go ahead. Carry on. I'm interrupting.
So I currently have 1.75 times 36. And I don't think I said what the other number would be. I double have to get 3.5 times 18. I
Okay.
don't think I said the 18. That's not helpful. And then I double half again to get 7 times 9, which is a fact that I know, 63.
Bam. So you're saying 1.75 times 36 is equivalent to
Yep.
3.5 times 18 is equivalent to 7 times 9, and they're all equivalent to 63.
Yep.
Y'all, that is mathing,
Yeah.
and we call that the doubling halving strategy,
Which is
which
really a
terrible
not,
name.
I mean, yeah.
Because notice that Kim didn't just double half. You kind of kept going, but you could have quadruple quartered.
Right.
We could bring in other problems where you might want a triple third.
Yeah.
I don't know if you can say that. Is third a verb? Triple and find a third. So doubling and halving is a great strategy that to do early with kids, because kids double. Doubling is a kind of a young thing that we can do early in developing multiplication. And then that can lead to doubling and halving. Let's talk about why doubling and halving is one of, I'm not going to say the most, but one of the most sophisticated multiplication strategies. Kim,
Yeah.
give me one. What's one? What do you got?
So it's definitely in the family of creating equivalent problems, which is a big idea. So you're thinking about a problem that would be equivalent in this case, we talked about it on an area model. So it's maintaining area. You're having to think about both factors at the same time. When you double one of them, what happens to the other one?
Yeah.
Yeah.
Yeah. And
And
that requires simultaneousness, right?
yeah,
Like
I was going to say, so
simultaneously
one of the
considering.
things you think about, people ask us, like, how do kids know which number to double and which number to half?
Uh-huh.
I don't know that we've mentioned that at all. And so my response to that is let them go at it. And they get to a point where they start to generalize the kinds of numbers that make sense to double or to half.
Mm-hmm.
In the beginning, when students are tinkering, they are not amazing all the time at it. And so rather than tell them these are the kinds of numbers, we would prefer that you use problem strings, right, to help them develop the idea, but then let them double and half or quadruple and find the fourth of 4 numbers. And then they get to a point where they go, oh, that was not helpful. Let me back out of that and attempt something else.
Yeah, like pause and don't dive in to save too early. Give them a
Yeah.
chance to go down a rabbit hole a little bit,
Yep.
back out, try something else. And that is mathematical behavior.
Right.
Mathematicians try things that make sense to them, and when it doesn't work out so slick, then they back up and try something else. And
Right.
that's a mathy kind of thing to do. Very nice. So, main things that are key indicators of sophistication are that we have to anticipate. And so, like you said, in order to think about finding an equivalent problem, I think that even has to be an idea, right?
Right.
Like
Right.
think about students who were taught, here's how you multiply, do these steps. All they're doing is like, oh, it's multiplication, I must now do these steps. And they just start doing the steps. What they don't do is say to themselves, what do I know? And could I think about this anticipation? Could I anticipate creating an equivalent problem? Can I think of a way to create an equivalent problem that would be easier to solve? That very idea takes bandwidth. How do we create that bandwidth? It's by developing multiplicative reasoning, developing the kind of reasoning, doing all of the strategies before, so that kids can start saying, oh, I can actually anticipate. Can I create an equivalent problem that would be easier to solve? So anticipatory thinking, equivalence, like you said, and the idea of simultaneously considering both factors. If I do this to one, how will it affect the other one? Ooh, that'll be nice. Let me
Yep.
try to go that way. Yeah, very cool. Let's see. The model that we used for this one was an area model. We've talked about how the dimensions and the area. We will also at some point start using equations.
Right.
So I'll be
Mine
honest
kind
with
of
you.
shifted along the way.
Yeah, by the end of it, I was writing equations and between numbers. So for example, on the 1.75 times 36, I have a double. I have a kind of an arrow with the times 2 from the 1.75 to 3.5. And from the 36 to 18, I have a kind of an arrow and a divided by 2. So if I doubled the one, then I halved the other. Every once in a while, I have a high school teacher say, but wait, if you do something to one side, shouldn't you do the same thing to the other? So then we have to discuss what sides mean. Sides of an equation, yes, but this is not an equation, right? This is I have an expression, 1.75 times 36. And then I've drawn arrows between expressions with the times 2 and the divided by 2. So that you might find that interesting.
Mm-hmm.
Yep, cool. All right. What else do we want to say about doubling and halving, Kim?
Well, it's an equivalent strategy, right? So we've been recommending that it's great to do some relational thinking
Oh, yeah, the
problems.
instructional routine, relational thinking.
Yeah.
Fantastic. Okay, so I've got one for you, Kim.
Oh, goodness. Okay.
Thanks for reminding me. What if we had a relational thinking that looked like this? 16 times 3.5. So I'm writing a horizontal equation. 16 times 3.5 equals 8 times blank. 16 times 3.5 equals 8 times blank.
I'm going to say this in a way that I don't think we've said. So you might have to clean up my language.
Okay.
If we have 16 3.5s, and I know that I don't want to deal with the 3.5s, I want so I'm thinking about it in terms of like, I have 16 of the 3.5s.
Yeah.
So I want to have the size of my group being twice as big. So I need half as many of them. So what I'm thinking about is I don't want to deal with 3.5s. I want to deal with 7s. And because the size of that group, the size of that number is twice as much, then I only need half as many of them. I don't know if we've said that here this way. So I'm thinking about 8 times 7.
Yeah, we didn't say it here. I almost wonder if you kind of thought a little from the answer when you said that, because the blank was the 7, and you kind of talked
Oh,
about it.
so yeah, I wrote it down and then I forgot which one was the blank. So then sorry, I just wrote 8 times 7 and then I forgot which one you asked me about. So scratch that. I need, which one was the blank? The 7 was the answer.
Seven's the blank.
Shoot.
7's what you don't know.
Okay. So then I want half as many groups of whatever, then they need to be twice as big.
Yeah. And y'all, you might want to write that down to be able to follow that. If you have 16 times 5 equals 8 times
3.5,
something.
3.5.
Oh, sorry.
Yep.
If you have 16 times 3.5 equals 8 times something, the 16 to the 8, you're saying I started with 16 of something.
Uh-huh.
Now I only 16 groups. Now I only have 8 groups.
Uh-huh.
If we're going to stay equivalent, the groups have got to get twice as big.
Yep.
It almost doesn't matter what the 3.5 is in this reasoning, right? If I've got 16 groups of something and I've got to have an equivalent total, and now I only have 8 groups, I got to have twice as much stuff in each of those 8 groups in order to have, in order to stay equivalent. So twice 3.5 is 7. Is that right? That was funny. He didn't remember what the question was. Good job, Kim. All right, y'all, you can actually find more of these relational thinking types. We put them out on social media all the time. We gather them, stick them on the website. So you can go to mathisfigureoutable.com/relational-thinking, or just Google it. Google math is figureoutable and relational thinking. And you can find examples of lots of these guys that you can use with your students. So you might be interested to know that we, when we did the addition one, we said most sophisticated addition strategy, give and take. When we did subtraction, we said most sophisticated subtraction strategy, constant difference. When we're doing this doubling and halving strategy today, we're saying it's one of the most sophisticated strategies. Why?
Yep.
Because it has those hallmarks. It's an equivalent strategy. It requires anticipatory thinking. There is simultaneity involved. However, there's one that is even more multiplicative. So as multiplicative as this strategy, doubling and halving, is, it is really the precursor to the most sophisticated multiplication strategy we think kids need to learn, which is flexible factoring.
Yeah, super fun. And, we're already kind of long. So let's just let them know that we've talked about flexible factoring on episode 153. So we highly recommend that you check that episode out to maybe tackle a strategy that might be new for you, or to strengthen that strategy if you've already heard of it.
Yeah, and when you do, think about, does it have those 3 things? Does it require simultaneous thought, and anticipatory thinking, and is it about finding equivalent problems that are easier to solve? There you go.
Yep.
So in this series, we're talking all about equivalence problems, finding equivalent problems that are easier to solve using equivalence. So, Kim, there was a time when I was working early. Hey, I made a lot of mistakes when we did this early stuff. I learned so much. When I was beginning to work with teachers and we were developing and I was thinking and all the things, one day I said, wouldn't it be cool if we have video of teachers doing these things with kids so that other teachers who are new could go, oh, that's what it looks like.
Yeah.
Well, I mean, we've now created the problem string hub in our membership site called
Yep.
Journey, where you can do exactly that. But in this moment, we had a few teachers who were kind of leaders. They'd been on the cutting edge. And so we said, would you mind, you handful of teachers, I'll come in with a camera and I'll video you and then we'll show everybody else. And the teachers were like, oh, we're a little nervous, but yeah, we'll give it a try. One of these teachers, I walked in the door, I set up the camera and she said, okay, is everybody ready? By the way, I will never share this name because your name is safe with me. And so
Yeah,
if there's
absolutely.
something that we're going to kind of poke at a little bit, I won't tell you who it is. But one of those teachers, is, are you ready? I was ready. The camera's all ready. She goes, okay, all right, here we go. She took a deep breath. She goes, students, today you're going to learn the doubling and halving strategy. Everybody write that in your notebooks. Doubling and halving. Okay, that's what we're going to do today. Ready? Here is the problem. 24 times 12. 24 times 12. Okay, is everybody? Oh, sorry. Actually, it was 12 times 24. My bad. It's 12 times 24. She goes, okay, everybody write that down. Here's how you do the problem. Everybody ready? Ready? You double the first number. All right. What is double 12, everybody? I'm in the back of the room going, is she just telling him steps to solve the problem? Like is she doing a non-example? Like I was like, what is happening right now? Because she was literally like telling them what to do. That's not how you do a problem string, right? You do a problem string,
Yeah.
you launch the problem, you see how kids are doing it. She's like step by step telling kids to do. Y'all, double the first number. So they dutifully did what she said. She goes, everybody double the first number. So double 12, that's 24. And then she said, all right, now everybody, now you have the second number. Okay, everybody do it. What's half of 24? Now it's going to be hard. It's going to be hard to half 24. Everybody work on that. I was like dying in the back, not laughing. I was like, what is happening right now? I finally just shut the camera off. I was like, let's just, y'all, 12 times 24, double and half that. You get 24 times 12. Then they kept going. Then they got 48 times 6. And then they got 96 times 3. And then I looked at her face. And she's like, oh, no, what do we do now? Because it didn't turn into this nice. She goes, let's practice on another one. And then she gave another problem. So then she walked around and she was like, nope, double that one, half that one. There was no discussion about which number she should double, which number you should have. There was no letting kids do. So problem strings, doubling and halving, all of these strategies are not about direct teaching steps in the strategy. It's about developing relationships in kids' heads so that the strategies become natural outcomes.
Yeah. Yeah. And I'll add, we'll go back to the story at the beginning. This is a perfect time because the kid in the class that I was filming had heard double half, right? Somebody along his journey had said, this double half, this is what you do. So if direct teaching is what you do, you might get the response like this kid at the beginning, where he's heard a thing and he's like, I don't know why you would do that. But towards the end of the problem string, and remember, we have this on film, we have video of him when I posed a problem, and we can hear him gasp a little bit and go, oh, so the reason why you'd want to do that is, and then he talks about creating an equivalent problem that was easier to solve. He had an experience that forced him to think about why you would want to do that when it might be useful. And it turned into a lovely video because you could see the learning occurring right in that moment. Yeah. And
Yeah, it was
that's the goal.
so cool. It's
Yeah.
such a neat moment for him to like first be kind of like,
Yeah.
yeah, somebody's taught me doubling and halving, but I don't know why you'd ever want to use that.
Yeah.
Yeah, and the gas
Yeah.
was just
That's
brilliant.
pretty
And the
cool.
look on
Pretty
his
cool.
face, and yeah, so we're after that, right? We're after
Yeah.
like it actually we own those things. We know it's about reasoning, thinking, and in this case, creating an equivalent problem that's easier to solve. Yeah, super. All right, y'all, thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Thanks for spreading the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisforgettable.com/challenge. Join us to make math more and more figure outable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.